In this video, we're going to present three models. They're called the counting models. And the counting models are models that are discrete. So you can count things happening 1, 2, 3, 4. They're useful for building companies like Google or Facebook, in which we're counting, for example, likes and not likes, where we're counting the repeated incidence of a particular word. Okay, so if Facebook is selling political data to a political party, they might want to know how many different kinds of ways that party is known. So for example, if you're talking about a Republican Party, you would say, how many times do you see the word elephant? Democratic Party, how many times do you see the word donkey? Or how many times do you see the iconography of an elephant or a donkey? How many times do you see a name associated with a Democrat politician or a Republican politician? And so there are people who are programming at Facebook, for example, and they will be counting how many different times they see the word of a political issue or a political person running for a particular office, and they will count how many times and what kinds of accounts these words repeat, and they can then measure where an ad might have more impact, positive or negative, to either get out the vote or to suppress the vote, which every political party engages in, getting out their vote and suppressing their opponent's votes. And so that's how Facebook, for example, might be a platform in which they can sell this information to political parties for money, and also for intelligence regarding where to place political ads effectively to get out their vote and to suppress their opponent's vote. Other examples of this is looking at social influencers' Facebook accounts and noticing how many times a particular color of eyeshadow appears. And maybe you see this eyeshadow appearing more and more and more often in association with a particular social influencer account. And thus you might then spot ads that enable the increased sales of a particular eyeshadow or a particular product. So you might be seeing, for example, right now, more ads with face masks because everybody's buying all kinds of fashionable and functionally superior face masks for one thing or another. So counting is a very important activity that is value added for advertisers and for people who sell advertisers data, and that's primarily what Google and Facebook use as a source of revenue, the intelligence they get from people's interactions to create this. So counting models are really, really valuable as a means of seeking employment in any company where counting is essential. Tesla wants to know how many engines have passed quality tests. Any electrical engines have passed quality tests so that they know how many cars they can build with these drive units that have electrical Tesla motors. Boeing wants to know how many different bolts they can produce per hour that are used to create riveting around engine supports. And any company, every company, and every person is interested in how often something occurs. Counting models are there to help you measure how often things occur. So in the case of counting models, count. That's what they do. Counting models count. So X in a counting model refers to a number of times something occurs, or a number of times something doesn't occur. And they're all based on something called a Bernoulli trial, after Jacob Bernoulli, a thinker, philosopher, Swiss, who came up with the story. And a Bernoulli trial refers to an event. Draw a tree diagram of a Bernoulli trial. It's an event, and this event has two possible outcomes. One that is usually referred to as what you're looking for, i.e. what you're looking for would be a success. And what you're not looking for, the opposite, the complement, is a failure. So we usually call one of the two outcomes a success, and the other outcome we call a failure. And we usually refer to the notations of the probabilities of success and the probabilities of failure as P and Q. And not only that, but P plus Q must equal 1, because that is a complete story. Either something that we're looking for happens or it doesn't happen. And that's what a Bernoulli trial is. What X does, then, X could be a count of the number of times you fail until the first success. That's called a geometric count. Geometric count of trials until your first success. So that's going to be one of the models we study, the geometric model. A second model under study will be called the binomial model. In the binomial model, X represents the number of times you observe successes, the number of successes in a finite number of trials that is preset or known. And we use the letter N to denote the total number of tries. So imagine a situation where you are playing basketball, exercising, you take the ball and you stand at the foul line and you take 10 shots at the basket. X would then count how many of the 10 shots you make. So how many successes you have out of N, i.e. 10 trials. So that's what a binomial model counts. How many times something happens out of these many trials. That would be called a binomial value of X. So you need two parameters to make this work, as opposed to just one for the geometric model. So a binomial model requires the number of tries and the probability of success. The probability of failure is automatically the complement of a success. Knowing P helps you know Q. The last model is called a Poisson model. By the way, you have separate notes for a binomial story, a geometric story, and a Poisson story in your Canvas notes. In a Poisson model, X is equal to the number of successes when all you know is the rate of success. And usually we use a Greek symbol for the letter L, lambda, and that Greek letter L, lambda, is the rate of success. So in this case, the Poisson model will only give you information about this rate of success, lambda. And you don't know the probability in a Bernoulli-based system. Okay. Now, in these three counting models, the way we compute expectations and the way we compute deviations is going to be manual. It's going to be using data compute expression in these models. So first, notice that I will put a list here of given information. So what's given for a geometric model is the letter P, the probability of a success, and de facto you're going to know Q. N and P are the things that you know in a binomial setting, the number of tries and the probability of success per try. And then the letter alpha, lambda, So I'll just put the letter L as the only given. So that's what's given. And then the way you measure expected values in these three models, the expected value of X is by the following formulas. It is 1 divided by P for the expected value of a geometric model. That would be a shortcut to the sum of all the weighted average values of X. In the binomial case, it's N times P calculates the expected number of successes. And in the Poisson model, it's the same L that gives you the expectation. And then to calculate the standard deviations in these models, what you're going to have to do to calculate the standard deviation in these models is you're going to have to take the square root of Q divided by P squared. To calculate the standard deviation in a binomial, you take the square root of N times P times Q. Remember, Q is 1 minus P, the complement of P. And then to calculate the square root in a Poisson model, you take to calculate the standard deviation in a Poisson model, you take the square root of the rate of success lambda. And so those 6 formulas that you have here are the formulas to calculate expectations and to calculate deviations in these counting models. So what are we going to do next? We're going to go into our lab 6 and look for examples of geometric, binomial, and Poisson models. So here we go. Switch over to our assignment list. Okay, so we're going to our assignments. We're going to quiz 6, lab 6, exam 3 types of questions. And we're going to try to distinguish between a geometric question, a binomial question, and a Poisson question. And then I'm going to open the calculators for these. So here's lab 6. Let me open lab 6. I'm going to go into question randomly here, question 2. No pun intended with the randomness. And then I'm going to go into question 4. Okay, so I'm going to take this question and all its parts. And let's see whether, go to the whiteboard and add a new page. Hopefully I can type this here. There we go. So it says here, a salesman normally makes a sale. Okay, so making a sale is a success here. Closing a deal is a success here. On 75% of the presentations he makes. Okay, so that means P is 0.75 and Q would be 0.25. We're going to assume that each kind of sale is independent of the other. And then we're going to find the following probabilities. So the first question here is, the failure to close for the first time on his 6th attempt. And notice how the language here, the first time, that implies that we're looking at a geometric count. So things happening for the first time, his first presentation, that's all indicative of a geometric counting model. Because we want to know when the first time that something happens is. Okay. So in this problem, all components of this question are geometric. So now let's look at the text of ABCD. So in the first case, we're looking at x being equal to 6, but it's about failing to close. Okay, so we have to be careful with the language here. And notice that we're talking about failing to close. Whereas here we're talking about closing. So in the first problem, the probability, that is the probability P, is 0.25, because that's the chance of failing to close the sale. Whereas in problem 2, we're talking about x being 5 and P being 0.75, because we are talking about making a sale, not failing to close the sale. And that is also the case for parts C and D. We're looking at closing a sale on his second attempt. The second attempt would be x is 2, and P is again 0.75. And part D says the first presentation he closes will be one of the first 3 attempts. So x is going to be 1, 2, or 3, less than or equal to 3. And P is going to be 0.75, and we're talking about closing a deal. So once I have an outline of every single calculation that I'm going to make, I'm going to go to Stat, Calculators, Geometric. So now I'm not going to use the custom calculator anymore. I got to use the geometric calculator, and I'm going to talk about the geometric in the context of number of trials. And once I do that, then I'm going to set P and X as in each of the cases indicates. So that is my job. My job is to first outline what I'm going to be doing in STATCRUNCH, and then put the command in STATCRUNCH that calculates these 4 things. So let me go to STATCRUNCH now. And you can leave in STATCRUNCH everything you have here. It won't affect the calculations performance. And then just go Stat, Calculators. As you can see, when you go to geometric, there are 2 kinds of geometric calculators. One is called number of failures. What that is the count of the total number of failures before your first success. I prefer to use geometric number of trials because geometric number of trials includes when the first success happens. So what I'm going to do with this geometric calculator, so notice how it's called geometric, that's how you distinguish it from the custom and from every other calculator. is we're going to use it in standard mode, and we're going to set this equals to whatever our problem asked us to set it equal to. So I'm going to set this equal to 6. And the probability of not closing a deal is 0.25. And the reason I set this to 6 here is because equal to 6 is because in the whiteboard, x equals 6 and p equals 0.25. So I'm working on part A here, on the part A computation. And the answer to that is almost 6%, 0.0593. So if I go back to my assignment in StatCrunch, sorry, if I go back to the problem at hand in the lab, in the question, okay, now that I reopened the question, the problem changed. So let me show you how it changed. It says here he fails to close for the first time on his 5th attempt. So now x is going to be equal to 5, even though p is still 0.25. So I'm going to go back to opening StatCrunch and go stat calculators geometric number of trials. And I'm going to set the probability to 25%, and this equals to 5, and get a different answer, 0.0791. And when I put here 0.0791, I get the answer and it's right. And I don't have to worry about the highly complex structure of rules of probabilities to compute this by hand, and it's less time consuming. So I know that there's an 8% chance that if I'm a good salesperson who closes 3/4 of their deals, and usually 1/4 of customers don't buy from me, the first time that I will see a non-buyer being the 5th time. In other words, I close a deal, I close a deal, I close a deal, I close a deal, I fail to close the deal. That story has an 8% chance of happening. The next story says the probability he closes his first presentation, the probability that I don't make a sale, don't make a sale, don't make a sale, and then I finally make a sale, the probability of that narrative is going to be the probability of making a sale is 3/4, and that I make my first sale on the 4th try is only a 1% chance. It's a very low probability that I have to wait 4 clients to get my first sale. My first sale is probably going to happen right away. So 0.0117 illustrates the very low chance I have of it taking me a very long time to close a sale. Then what is the probability that the first closing happens on the 2nd attempt? To do that, I just go back to the calculator, and where I set 4, I set 2 now. That's almost 19%, 0.1875. So then I go back to the lab and I put 0.1875. And then the probability that the first closure is one of his first 3 attempts. So it could be on the first time I sell, or the 2nd, or the 3rd, or. So every time you hear the word or, you're supposed to be adding probabilities together. Just like every time you hear the probability of this and that, you're supposed to be multiplying probabilities. Therefore, in this case, one of the first 3 attempts being a sale, means that I'm going to change this to less than or equals to 3. And that is a very high probability because it's very likely that I'm going to close my first sale deal on one of the first 3 attempts, 0.9844. So going back to the problem, I put here 0.9844, and that should also work very well. So this is how you use the geometric calculator in problems in your lab and in your quiz and in your exam. You look for language about the first time, the first time, the first time, and that is indicative of a geometric model being used. Next is a model in which we're looking for an application that could be binomial, or it could be geometric. And here's one, problem 6. A manufacturer of game controllers is concerned that its controller may be difficult for left-handed users. So they're going to try and test these remote controls for games on both lefties and righties. They tell us that about 14% of the population is left-handed. So about 86% is right-handed or other, maybe ambidextrous. So 14% are lefties, 86% are non-lefties. Now they take a group of 5 customers. See, that's something new, something we haven't explored in problem 4. Here they're telling you the total number of people that they are randomly testing the controls on, 5 customers. So that's a preset for a binomial kind of count, because they're not only giving you the probabilities of lefty and non-lefty, of success and failure of 0.14 and 0.86, they're also already telling you that the number of tries is going to be 5. So then in a group of 5 people, you know, what's the chance that you have 1 lefty or 2 lefties or 3 lefties? That kind of question is binomial. The first question, though, asks you about the first lefty being the 4th person. So for the first lefty to be the 4th person, you'd have to have a righty, a righty, a righty, and then a lefty. Okay, so this probability would be a righty and another righty and another righty, and then comes the lefty. But rather than do the arithmetics of this in this fashion, what we're going to do is remember that anything about a first lefty is a geometric question. So we're going to go back to our geometric model. We're going to set the probability of a lefty occurring being 0.14, and the chance that the first lefty is the 4th person is 0.089. And that means that our answer to our homework question here is, this is 0.089. Now I'm not going to leave this answer with my work showing. I have to just put the answer. So the next question is, there are some lefties among the 5 people. So this is our first question that doesn't relate to the first time I see a lefty or the first time I close a sale or something like that. This is about some lefties in the group of 5. This is a binomial question. So how do I express some lefties? The answer is, in algebra, you say X is more than none. So some lefties means that you have 1 or more lefties. Some lefties means you have more than 0 lefties. And so we're going to use X greater than 0 to express some lefties among the 5 people. Okay. Another thing that I need to remember is that I'm going to be using the calculator called binomial. And when I open the binomial calculator, I'll be able to set n, and I'll be able to set p to these two parameters before I do the calculation of x greater than 0. So let's go back to StatCrunch for a moment and open a calculator called a binomial calculator the first time here. And in this binomial calculator, n, the number of repetitions is going to be 5 selections. 14% is the probability of a lefty. And I want this to be greater than 0. Because greater than 0 is how we say we could have 1 or 2 or 3 or 4 lefties. And the answer is 0.53. This is what that rounds to, 0.53. So I'm going to go here to the lab, the assignment, and change this to 0.53. Check my answer. Well done. The first lefty is the second or third person. So we go back to the notion of a first lefty, i.e. a geometric model. Now you can see why I do not close calculators when I open others, because I might have to refer to using them again. Since the question was about the first lefty being the second or the third person, I'm going to use the calculator now in a different way called a between way. And I'm going to look at 2 to 3. And notice how the red color identifies the second and the third bar of this geometric model. And 0.2239 becomes the answer to the probability that the first lefty is either the second or the third person on the list. And then when it says there are exactly 3 lefties in the group, we're no longer talking about the first lefty. Now we're talking about a group of lefties in the group of 5. And so I have to go back to the binomial calculator in this case, and 3 lefties exactly would mean x equals 3 out of 5. And that's a very low probability. It's 0.0203. 2% is a very low chance. So we go back to the assignment and put here 0.0203 and check the answer. And of course it's right. So this is how to distinguish the geometric and the binomial counting models. In one model, we're counting when do we see the first instance of something we call a success, the geometric model. Another, we count how many total successes in a finite known number of tries, the binomial model. My last question that I'll work on is something called a Poisson model. And in a Poisson model, you are not given the probability of success per try. You don't know how many tries you have. All you're given is a rate of success. So in this case, they're telling you that 2.7 people per minute check out their shopping carts from, say, an Amazon.com or Walmart.com type of site, an e-commerce site online. And the analyst believes that each purchase that each purchase is independent of any other purchase. So advertising isn't having an effect that's differential on one person versus another and whatnot. So here we're looking at, if you're a user experience type of employee, you would go to work by turning your computer from home and seeing all these sales happening in the products lines that you're responsible for. And then you would see 2.7 shoppings per minute. And so that's what we call a binomial model. So if you're counting something, i.e. you're counting sales in this case, and you're not given n or you're not given p, the probability per try per person of checking out or not checking out, and how many people are doing that in a minute of time. Chances are you're not looking at a binomial or at a geometric, you're looking at a Poisson counting story. And then they ask you, what is the probability that in any 1 minute, at least one purchase is made? So the way we use STATCRUNCH to help us facilitate the math is we open the Poisson calculator, Stat Calculator's Poisson, and we switch the mean to 2.7 because that's what the number of sales are in 1 minute, and then we choose at least one sale. So we go greater than or equals to 1. That's what at least 1 means. And we get 0.9328. And that's the right answer. The next question is, what is the chance of seeing no sales in 2 minutes? And this is something that is a little tricky. So again, let's read the question. No sales in 2 minutes. So when we look at the Poisson calculator, no sales means that this should be a 0, equal to 0 exactly. No sales in 2 minutes means that since 2.7 sales happen in 1 minute, I'm going to multiply that by 2 to see how many sales I would have expected in 2 minutes. And I can leave that expression there and the software will do the math. I'm going to change that to the numeric value that is correct, just for the sake of finishing the problem and you noticing the difference between doing a calculation per 1 minute and per 2 minutes. So in this case, 2.7 times 2 is 5.4 sales in 2 minutes. Okay, so 2.7 sales in 1 minute is 2.7 times 2 in 2 minutes. If this had been in 10 minutes, you would say 2.7 times 10. You would have scaled the average to the number of minutes that you're computing for. And so in this case, there's a very small chance of not seeing one sale in 2 minutes. It's less than 1%. It's 0.0045. So I'm going to go to the lab and put here 0.0045. And good job, I'm done. I'm done with that question. And so that's how we use STATCRUNCH to calculate either a geometric probability, models where all we need is the probability of a success, and then we can use standard mode calculations that have one direction, either on the greater or less than side, that either include or not include the limits, or two calculations that have a lower and an upper boundary of counts in measuring the first, how many tries until the first time something happens. A binomial calculator tells us how many times something occurs, how many successes there are out of a certain number of times we try something. So it's successes out of trials, as opposed to the geometric model, which was how many times we have to try something until we succeed for the first time. In a binomial, we're counting total successes out of total attempts with a known probability of success and failure each time. And last but not least, the Poisson model helps you count how many times something happens, and all you know is the rate of success. And you know that that rate is scalable and that you can make it bigger or smaller by scaling factor so that you can measure probabilities on a different per unit of cases. And I hope this video is as useful as all the other ones at helping you complete your Chapter 6 activities. I am going to then stop the sharing and close this video. Thank you for watching.